All right. So good morning, everyone. So my name's Joe. I'm a postdoctoral research fellow at UCL, and I'm excited to be telling you about the status and results from the LUX-ZEPLIN dark matter search experiment. The talk will go something like this, where I'll start off with a brief overview of LZ as an experiment. I'll tell you about the results that we published last year for the WIMP search and 60 live days worth of exposure of the detector. And then we also published a paper this year looking for interesting physics in low energy electronic recoils. I'll give you a little teaser for what we have coming up in the pipeline before giving you some concluding remarks about where we are and where we're going. But before I jump into the meat of this talk, I want to first establish some context in that this is a direct detection dark matter search. And in order for us to do a direct detection dark matter search, we need to make some basic assumptions. The first of which is that dark matter conforms to the standard halo model. So that's an isothermal sphere of dark matter with a density that goes like 1 over radius squared. There's a local dark matter density of about 0.3 GeV per centimeter cubed. And then in phase space, this conforms to a Maxwell-Boltzmann velocity distribution truncated at the escape velocity of the Milky Way. And then as Earth moves through the galaxy, that results in a characteristic velocity of the distribution at about 220 kilometers per second. Now, in terms of the particle species, we're assuming for the most part that we're looking at weakly interacting massive particles, or WIMPs. So this puts us at about the GeV or TeV mass scale. These are also extremely weakly coupling to baryonic matter. So we're looking for very rare interactions. And some examples of a particle species like this are the SUSY neutralino or Kaluza-Klein dark matter. So again, assuming that there are any interactions with baryonic matter at all, it will almost always be in the form of a nuclear recoil. That's an elastic scattering event between the dark matter particle and the nucleus of an atom in our detector. In contrast to this, we have most of our backgrounds, which are in the form of beta decays or gamma decays, i.e. electrons and photons, and these are kinematically very limited in the amount of energy that they can impart to the nucleus of an atom, especially if it's a big one. So they are far more likely to scatter off of the atomic electrons in the atom, and therefore we call them electronic recoils. So that's the preamble for the context, and then I'll give a little shout out to my collaboration, the LUX-ZEPLIN or LZ collaboration. We are 250 scientists, engineers, and technical staff strong, spread across 37 institutions in 5 countries. I've given you our social media handles for Twitter, Facebook, and Instagram. You can go check us out. We also have our website up there. And then, of course, I have to give a huge shout out to our funding sources over here on the right side of the slide. But moving on into the detector of LZ, which is that of a dual phase time projection chamber, or TPC. Now, it's filled with liquid xenon as the WIMP scattering target, but being a dual phase detector, it also has gaseous xenon, but we'll get into that later. The total mass of xenon in this detector is 10 tons. But you'll see that we have within the TPC itself, which is about a 1.5 by 1.5 meter cylinder on the right of the slide here, that contains a 7-ton active mass. So when we say active mass, we mean inside the TPC. And furthermore, within that is a 5.5-ton fiducial mass, which is a central volume that we basically limit our scope of potential dark matter interactions to within that fiducial mass to reduce background contamination. Now, liquid xenon is an effective scintillator, which means that this instrument has to be decked out with some kind of light sensor. We've chosen the R11-410 photomultiplier tubes from Hamamatsu. We have 494 of them in total between 2 arrays, one at the top and one at the bottom. These PMTs are very sensitive to VUV scintillation, which is where liquid xenon is scintillating. And then the detector, the TPC itself, is made up of PTFE, which is highly reflective for this wavelength. So we're good at capturing the light and detecting it at the same time. Here's some more pretty pictures of the detector. We've got at the top right here, the fully instrumented bottom array of the TPC. We've got some students who are scanning the outside of the TPC wall for dust contamination using UV light. Down here, we have a PhD student who we haven't killed his spark for life yet. He's happy in front of the top array of PMTs that he's just finished wiring up. And all of this is 1 mile underground at the Sanford Underground Research Facility in South Dakota. So this is a picture that I took at the last collaboration meeting at SURF, Sanford Underground Research Facility. But we don't just go here for the pretty scenery. This is a top-notch research facility that's underground so that we can limit the amount of cosmic ray contamination in our experiment, as well as other kind of backgrounds that are intrinsic to running the experiment at the surface of the Earth. For context, or for comparison, trying to run a dark matter search experiment at the surface of the Earth, or one like this at least, is like trying to hear the drop of a pin at a Metallica concert. So that's why it's very important to go underground to limit those backgrounds. So as I said before, liquid xenon is a scintillator, and I'll briefly go through the microphysics here with some pretty pictures. So let's imagine that we have a dark matter scattering interaction with a xenon atom. Now, this is going to be an interaction on the energy scale of about keV, and that's more than enough energy to ionize that atom that got struck. But it'll also be more than enough energy to send it recoiling away through the detector, leaving a track of more xenon ions, but also excited xenon atoms, or excitons, at the same time. Now, those excitons will undergo a process called self-trapping. And what that means is that they will bind onto a ground state atom nearby, and that will form a sort of a molecule that we call a dimer, but that dimer will be in an excited state, and therefore we call that excited dimer an excimer. That excimer will relax down to the ground state via dissociation, so you'll end up with two ground state xenon atoms and then an additional VUV photon, and that VUV photon is what contributes to what we call our S1 signal. But that's not the whole story, because we also have those ions can undergo a self-trapping process of their own. They'll form a dimer as well, but it'll be a charged dimer. And if that charged dimer happens to collide with one of the electrons that's produced in this process, it can basically neutralize and become an excited dimer as well, and then also contribute to the S1 signal. But being that this is inside of a TPC, and when you use a TPC, you're usually using an electric field of some kind, most of those electrons, about 2/3 of them, will actually be stripped away from the interaction site and drift up towards the top of the detector, where the gaseous volume of xenon is waiting. So all of this is enclosed within a drift field of about 100 volts per centimeter, give or take. That's a kind of an order of magnitude estimate. And then once it hits the liquid gas interface, there's a gate electrode, which kicks up the electric field from hundreds of volts per centimeter to kilovolts per centimeter. And in that electric field, the electrons can accelerate very quickly and then undergo collisions with gaseous xenon atoms, which triggers a process called proportional electroluminescence. This is very similar to the scintillation mechanisms that I was showing before, but this is a sort of a secondary process that produces what we call our S2 signal. So that's essentially how the TPC works. So what does a typical signal look like when you put it all together? Well, let's consider again a dark matter interaction here. You'll have that first collision between dark matter and xenon, and that will produce your S1 signal. It's usually pretty small, around there, especially at these energies. But then sometime later, the electrons will have drifted up towards the gaseous volume of the detector. They'll undergo their electroluminescence, and then they'll create their S2 signal that usually looks a lot bigger. So this is basically what the signal looks like, and we can reconstruct everything that we want in the event from this information. So let's first look at position. So we want to establish the full 3D position of the event, and the first thing that we do is reconstruct the radial part of its position using the hit pattern of PMTs in the top array there. That tells us everything we need to know radially. And then given that we know the drift field strength, we can also know the drift velocity, and that means that the delta T between S1 and S2 gives us everything that we need to figure out where the Z coordinate is. And this all gives us resolution and position space on the order of about millimeters in general, which is absolutely critical for fiducialization. And fiducialization is the key step in mitigating backgrounds that are intrinsic to basically having any detector materials at all. So basically at the edge of the detector. The next thing we want to do is reconstruct the energy. So for that, we basically integrate the pulses, both S1 and S2 pulses, calibrate them to units in photons detected. So we basically want to get the number of photons that we found, and then that unit is also abbreviated to PhD for future reference, by the way. But essentially, the sum of those two quantities is all that we need to reconstruct the total energy of the interaction. Now, the next thing that we want to do is be able to tell the difference between a nuclear recoil and an electronic recoil. So for that, I want you to pay attention to the relative sizes of S1 and S2, because if this was, say, triggered by an electron rather than dark matter, you would have something that looks a lot more like this. So that ratio of S1 to S2 is a lot smaller for electronic recoils than it is for nuclear recoils. And to demonstrate this with actual data, here I'm showing you what our calibration data looks like in the standard S1 versus log S2 space. So we have two populations of events here. One is neutrons from deuterium-deuterium fusion. So these are monoenergetic neutrons that we basically fire into the detector. And then we have a tritium source, and by tritium source, I mean tritiated methane that we basically inject into the detector and allow it to circulate around. So these are clearly nuclear recoils and electronic recoils. I should clarify that neutrons are actually kind of a pesky background for dark matter searches because they look so much like dark matter. So they populate the nuclear recoil band, whereas the beta decays populate the electronic recoil band. And with this S1, S2 ratio space, we're able to reject 99.9% of electronic recoils because they basically are well separated from the nuclear recoil band. In addition to all of this, we also have what we call our anti-coincidence veto system. So there are two main components here. One, so just outside of the active TPC region is what we call the liquid xenon skin. So the TPC is housed in a cryostat vessel. And for electrical insulation between the TPC, which is at high voltage, and the cryostat wall, which is at ground, we have a gap. I can't remember off the top of my head how big that gap is, at least 3 inches or so. That gap is basically otherwise in vacuum and would provide that electrical insulation. But instead, we fill it up with liquid xenon and instrument that with PMTs as well. And this is useful for getting rid of gamma rays, which could interact near the edge of the detector and maybe not leave so much energy, but then scatter again inside the liquid xenon skin. And we could use the coincidence of those two signals to reject gamma rays that are maybe not so high energy due to Compton scattering. So in addition to that, though, because another problem is detector neutrons from radioactivity in the surface materials. Neutrons can travel a little bit farther, or a lot farther than gammas can, so they can potentially scatter once and then make it completely outside the detector. And for that, we have a sort of an acrylic vessel that surrounds the entire cryostat that's filled with 17 tons of gadolinium-loaded liquid scintillator. And gadolinium is a very effective neutron capture target. When neutrons are captured on the gadolinium, it will produce an 8 MeV gamma ray. And then since the gamma ray is produced inside of a liquid scintillator volume, it will produce a lot of light. And then all of that is surrounded by an array of outer detector or OD PMTs to act as the veto signal for those neutrons. And to demonstrate its effectiveness, we ran a simulation of the relevant neutron backgrounds for our WIMP search over a 1,000 live day run. And we found that, I mean, although we do get good self-shielding from the xenon being a dense target itself, you still have about 10.4 events in 1,000 days from just neutron backgrounds. But with the anti-coincidence veto, that background gets mitigated by a factor of about 10, which is absolutely fantastic for us. So with all of that, let's move on into the first science run, or SR1, which we published last year, but it was recently accepted into PRL. And I've been told to absolutely brag about the fact that we've gotten editor's suggestions. So, you know, do with that what you will. I've got the DOI here for you to check it out later if you want. I absolutely suggest you do. So that's the paper, and let's just jump right into the actual meat of that paper. So the first thing that I want to talk about is the backgrounds. So this is the key part of the analysis, is trying to understand the background components in our model, and then do a profile likelihood inference methodology to determine whether or not we found dark matter. So by far the biggest background that we have in this detector is from radon emanation coming from the detector walls. So how does this happen? Well, so you have uranium and thorium contaminants in pretty much everything on Earth. So we call these primordial radionuclides. They are just they're on everything. You can't get rid of them. And then within the uranium-238 decay chain is the daughter radon-222. Radon is a gas at room temperature, and that means it can emanate out from the surface materials and get into the bulk of the liquid xenon. And then radon itself has daughters that are pretty much all radioactive themselves. And then there are these two here, polonium or lead-214 and bismuth-214, that are beta emitters and can have energies that bleed down to the energy level of WIMP interactions. So these are the ones that we kind of care about the most. But bismuth is easily tagged because it's followed by polonium-214 about 200 microseconds later at a very well-defined energy alpha. So we can tag that pretty easily and mitigate its effect. But lead-214, is a beta emitter that doesn't have any well-defined backgrounds that are useful for tagging. So we call these naked betas, and they are actually the biggest background in our detector. In addition to this, so this is an electronic recoil background. We also have the sort of the thorium decay chain equivalent of lead-214 and lead-212, also a beta emitter. We have krypton-85 and a suite of radioactive isotopes of xenon, like xenon-124, 136, and 127. And then there are also an array of charged current solar neutrino interactions that all populate this electronic recoil band up here in S1, S2 space. In addition to this, we have the relatively short-lived argon-37 electron capture. This is a cosmogenically activated background. Now it's an electron capture, so that means it's usually followed by a K or M shell X-ray that's emitted at the same time, which is a monoenergetic feature in the electronic recoil band right on top of what we would consider our most sensitive WIMP targets. And then I've also highlighted coherent elastic neutrino scattering from boron-8. Now this is not, this is actually a signal in its own right. We have a search for that going as well. But if it's detectable, then it would show up as a background in the WIMP search right around here at the bottom half of the nuclear recoil band. So we include it in our background model. And the last background that I want to highlight is what we call accidentals. So these are accidental coincidences between unrelated S1s and S2s. So these can kind of fool our event finding software and look like a single scatter inside the TPC. So we want to get a handle on these for sure. The way that we do that is we first characterize the rate by looking at events that have something called an unphysical drift time. So you can imagine that if the delta T between S1 and S2 is so big that you would relocate its Z position below the TPC, you know that that can't be right. So that's obviously a random S1 and S2 that have just kind of fooled our software. So we use those events to characterize the rate and then extrapolate it to all drift times. And then the next thing that we want to do is characterize the probability distribution in S1, S2 space. And the way that we do that is something called a chop stitch analysis, where we basically take random lone S1s and S2s and stitch them together. And then we basically use that to characterize what this distribution would look like in S1, S2 space. And then we go through we've developed a series of cuts to combat this. We can reject them with 99.5% efficiency. And then in this search, we were getting down to an expected level of about 1.2 events in 60 days. Okay, so I'll try to hurry up here. So here's basically the data that we get after all of our analysis cuts are put in place. We have 335 events that survive those cuts and end up in position space distributed like this. Here you can really see the effect of the surface backgrounds from lead-214 especially. And that's why we fiducialize at about 4 centimeters away from the wall of the TPC, especially because as further out you go, the worse your position reconstruction resolution gets. And then in the bottom right here, we have the data as it appears in S1, S2 space. We actually don't cut anything based on these, or at least not directly, based on where the data lies in this plane. We actually analyze everything in this region of interest using a statistical inference method called the profile likelihood ratio. And this is a way of comparing your best fit model with and without signal. And what we found was that the data are exactly consistent with background only, where our best fit was 333 events and the number of events that we got was 335. So we didn't find anything but we did find the most nothing out of any experiment in the world. We're world leading for WIMP sensitivity across a mass range from 9 GeV up. And that's obviously very exciting for us. We're poised to keep that lead going forward and hopefully at least hold on to that lead or potentially discover WIMPs, but who knows. Anyway, so I'm going to quickly go through this low energy electronic recoil search. The gist of it is that we basically wanted to ask ourselves, is there anything interesting happening in the electronic recoil band? So signals that we considered were the interesting neutrino electromagnetic moments. So with certain extensions of the standard model, you can have radiative corrections that give the neutrino a small millicharge and a small magnetic moment. We can also look for solar axions, galactic axion-like particles, and hidden photons for signals that look very similar to the photoelectric effect, basically a resonant absorption of those particles to kick out an electron from the atomic structure of xenon. And then we also look for the Migdal effect. This is with ordinary WIMPs, but instead of an elastic scattering, we have an inelastic scattering, which, doesn't actually deform the atom like this cartoon shows, but it's basically a sort of a recoil that displaces the nucleus from its slightly from its electron cloud, and then in sort of returning back to equilibrium, there's enough energy to send out an electron for an event that we can analyze. So I'm not going to go through the analysis because it's in fact exactly the same except for a different signal hypothesis as the main WIMP search. I'll sort of start off by saying we didn't find any evidence for a discovery or any significant evidence for a discovery. So we're setting upper limits on all of these. For the magnetic moment of the neutrino, LZ posts an upper limit of 1.36 times 10 to the minus 11 Bohr magnetons. In this space, we're still very well constrained by astrophysical measurements, especially from globular clusters. But in the space of neutrino millicharge, LZ is actually world leading. So we're excited about that, of course. We posted an upper limit of 2.24 times 10 to the minus 13 electron charges in this space. Moving into axions and hidden photons, we were unfortunately not world leading in any of these spaces, but we're very closely following behind xenon n-ton. And then in the space of solar axions, we're closely behind xenon n-ton, but still everything is much better constrained by red giant star measurements. A key point here that I want to highlight is that we were background limited in all of these spaces due to the presence of argon-37, but argon-37 has a half-life of about 35 days or so, so it's all gone at this point. So future searches for low-energy electronic recoils, especially the axions and hidden photons, are going to be a lot less background limited in the future. So hopefully we can make up some ground or maybe even pull ahead of xenon n-ton in this regard. Lastly, I'm going to quickly go through the Migdal effect. So the Migdal effect actually has 3 searches associated with it, as does the main WIMP search. In that there's a spin-independent channel and then 2 spin-dependent channels, one where the WIMP is coupling to neutrons and protons. We are world leading in the case of spin-dependent neutron coupling across a mass range of 1 to about 3 GeV. And in the spin-independent case, actually, as I was making this presentation, we were world leading for a little while. But then Darkside 50 actually got their paper published, wherein they showed that they are in fact world leading. But there's still some questions to be answered about the liquid argon nuclear recoil response there. There's some pretty big uncertainties. So whether or not they're this far ahead of us remains to be seen, but that's kind of where it stands right now. In the future, it might not look so big of a difference there. So I'll quickly start wrapping up here. So these are some papers that we have coming up in the pipeline. So we have non-relativistic effective field theories. So basically, this is a model agnostic approach to looking for WIMPs, because there's more than just the spin independent and spin dependent interactions that WIMPs could possibly have with baryons. And this could extend over a much broader energy range. So we're studying that. We're also looking for ultra heavy dark matter. And I believe I have a typo. We're actually looking, it's not 10 to the 6 GeV, it's actually more like 10 to the 19 GeV is what we're looking at for Planck scale dark matter. And the interesting thing about this is that when you have dark matter at this high of a mass scale, you're actually not sensitive to cross sections down to the level as low as ordinary WIMPs, basically because you're limited in sheer number that you can have and still maintain the correct relic abundance of dark matter. So this could potentially look like an event topology with multiple scatters in the detector. So we call these multiply interacting massive particles, or MIMPs. We also have a radon tagging veto paper that we're working on. This is actually really important for the main WIMP search because, like I said, lead-214 is producing those naked betas, but they do come with a radon-222 alpha decay immediately before it. So we're trying to use that as a coincidence veto tagging. It's a lot more difficult than bismuth and polonium-214, but it potentially can be done, and that's what we're working on. And then, of course, we also have a muon flux measurement. Virtually every dark matter search that I know of usually comes with at least an attempt to measure the muon flux in their laboratories. So that's what we're doing, characterizing the muon flux during SR1 and then comparing to simulation models. Right, so I'll wrap up here with the concluding remarks that we're world leading in the main WIMP space with just 6% of our total planned exposure. The low energy electronic recoil search we're world leading in 2 out of 8 of those spaces, but again, we were extremely background limited due to the presence of argon-37, among other backgrounds that were very short-lived and won't be there in later searches. So hopefully we'll gain some ground or take the lead in some more of those spaces. And then all of this is coming with the statement that we're going forward to 1,000 live days, or that's at least the aim. And this is going to push us deep into potential discovery territory. So hopefully, we can finally solve the dark matter problem. But in all likelihood, we're just going to not find, or we're going to continue to find the most nothing, and maybe even put some more work towards closing the book on WIMPs. But anyway, that's my time, and I'll take your questions.